Today we're going to be graphing the other four trig functions that we haven't yet. So we've been focusing on sine and cosine. Today we're going to focus on tangent, cotangent, secant, and cosecant. And let's just jump right into it. There's a little bit more graphing to this one than yesterday, so not to throw you off, but we'll see how it goes. With tangent, let's start off with the finishing off the trinity of our trig functions. Tangent, if you remember, is opposite over adjacent or y over x, and this creates an issue. So sine and cosine both could be any value, or you can plug in any angle, but tangent has undefined slopes, or there are undefined slopes out there, primarily when cosine is 0 or when x is 0. We get into this little trap. So at pi over 2, there's an asymptote. Also at negative pi over 2, there's an asymptote, because those are the first two, or the closest points to 0 that x is 0. So tangent across the x-axis is 0, 0. There's going to be a slope of 0. And halfway between those would be at pi over 4, so that's when sine and cosine are the same value. Sine of pi over 4 divided by cosine of pi over 4 is going to be 1, and then same thing with the negative. So they're the same but opposite, so it's going to be negative 1 at negative pi over 4. And all of this together, we're going to see that the period is pi. So with sine and cosine, the period's 2 pi. With tangent and actually cotangent, it's going to be pi. So when you do those period calculations, instead of 2 pi divided by omega, it'll be pi divided by omega. So you might add that in there. Add that stuff to your purple sheet. Just make sure you have the properties of it, especially the period of it. With asymptotes, this gets a little bit different, as you might expect, but the nice part is we don't have too many nice coordinates of tangent, so a lot of it's going to be estimation when we get into graphing. You might separate this out a little bit, but my strategy in general is I'm going to do red for my asymptotes. Taking all the asymptotes and marking them, I'm going to set 4 units for one period. So this is negative pi over 2, this is pi over 2, and then count out 4. 2, 4, and then 2, 4, 2, 4. So the red lines are going to be my asymptotes. 2, 4. And then we won't be able to fit some of those in there. At 0, 0, it's going to be at 0, or sorry, it goes through 0, 0, because sine of 0 is 0, and it's sine over cosine. So 0 over 1 is 0. Same thing at, this is going to be pi sine of 0, 2 pi sine of 0, 3 pi, 4 pi, 5 pi. I'm going to mark this as pi over 2. So my scale is going to be pi over 4 to 1. And then I'm going to say that this is 1 and this is negative 1. That kind of helps guide you or show your asymptotes a little bit better. But since this is pi over 4, this is where sine and cosine are the same. So sine divided by cosine is 1. Negative pi over 4 is negative 1. And from there, kind of just go with it. So it's going to be, it kind of looks like a cubic. It's not a cubic, especially because it's repeating itself, but it has that kind of form. Cubics don't have asymptotes. They just grow really quickly, sooner than other functions. But you're just going to repeat it. So pi over 4 away from the 0 or the x-axis, and fill in the gap. Boom, boom. Ka-chow. Boom, boom. Boom, baby. And then keep going. This one we can only fit half of, but we do have the other half over here. Okay. So it does repeat itself. The only thing with this is it's not continuous, and it's extremely not continuous just because it has so many different asymptotes. But those asymptotes also repeat themselves just every pi away. But we can still transform within tangent and the other functions. So let's see what we got. That number outside of this of the trig function is your amplitude, or it's your vertical stretch. So this is a vertical stretch times 2. So it's going to be 2 times as high. Amplitude doesn't quite make as much sense with these just because it's not a distance away from, it's not a maximum distance away from the midline, because we get all real numbers for our range, so it doesn't quite make as much sense, but it grows 2 times as fast. Negatives still reflect, so this is a reflection over the x-axis for that vertical movement, and then this the plus pi over 4 is a horizontal shift pi over 4 left. It's left because we're adding. If we were subtracting, it'd be to the right. Cotangent is going to be the reciprocal of tangent. So the same rules apply. It's going to have, since tangent's repeating itself every pi units, cotangent's going to be repeating itself every pi units. So the period or the cycle is still pi. The values are just going to be the reciprocals. So it looks very similar, but it is different, has a lot of the same characteristics though. This time it's discontinuous or has a vertical asymptote whenever y is 0 or whenever sine is 0 essentially. Can't be divided by 0, so whenever sine is 0 we're going to have a vertical asymptote. This time x or cosine whenever it's 0 is when it's hitting the x-axis. So cosine is 0 at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2. So you're just going to come up with all of those. Sine is 0 at all of these places. So 0, pi, 2 pi, 3 pi, 4 pi, any full number of pi. So that's where cotangent has its asymptotes instead. Graphing cotangent, again, it's going to have a vertical asymptote starting where sine would be 0. Sine is 0 at 0. So here, I'm going to leave the same amount of space, but at pi, sine is 0, so cotangent doesn't exist. At 2 pi, at 3 pi, 4 pi, and 5 pi. Also negative pi. Don't forget the left-hand side of that. It's important too. Halfway between, we're going to have our 0 mark. I'm just going to mark this as pi, 2 pi. Halfway between, we have our 0, or our x-intercept. So all of these are x-intercepts just halfway between the two, unless it's been shifted up or down. Okay, so at pi over 4, we have cosine of pi over 4 divided by sine of pi over 4. Because of that, we have same number divided by the same number, or 1. Over here, we can look at, so this was pi over 4. At 3 pi over 4, we still have the same values, just they're the opposites. So it's going to be negative 1. Flipping that is still negative 1. So this time, instead of 0, or instead of an asymptote, we just have 0. But now these are the portions that are connected to each other. So cotangent just looks like tangent but flipped. Okay, so that's what we're repeating every time. Sorry, I forgot to scale this, but 1 and -1, same scale as before. Let's get it over here since I'm over here. That value. That value. And the nice part about this is if you're ever stuck, you can always type these in your calculator to confirm it. I'll show you how to type cotangent and the other cosecant and secant into your calculator, but you can always just check to make sure you have the right answers by plugging in numbers. So good way to check, but much slower if you have to do it that way. So the graph 2 cotangent 3 of x compared to cotan of 3 of x, that 2 is our amplitude or our vertical stretch. So vertical stretch times 2, or 2 times growth, or in this case decreasing rate. 3 is omega, so pi divided by omega is our period. But it doesn't really ask for the period, it just asks for how does it compare. So it is horizontally compressed. From pi to pi over 3, it's by 1/3. So compressed by 1/3. I'm not going to be too picky on how you phrase this, but compression of 1/3 or stretch of 1/3, those to me mean the same thing. I would prefer you say it's compressing since it is compressing, but some might find that as a double negative, so it gets a little tricky the way you phrase it. But horizontal compression, it's 1/3 of the size horizontally, and it's twice as high, or twice as far from the original state. Cosecant is the reciprocal of sine of x. Sine of x is continuous, there's no issues with it, but since it is the reciprocal of it, sine of x does equal 0 every now and then. Case in point. So cosecant is going to have the same exact asymptotes as cotangent, because that's where both 1 over sine and cosine over sine will have 0 as the denominator. So it has asymptotes. It looks a little different, and it's kind of cool. You actually use sine to come up with cosecant. So first you're going to sketch sine here. And I'm going to do this in red. You might do it in dashed, but just regular. I'm going to squish it a little bit, that way we can see more of cosecant. I'll show you what I mean in a second. Still going to spread these out, so this is going to be pi over 2. This is pi. That should be enough to get our graph. So again, every 2, I'm shifting 1 up or 1 down, just continuing that pattern. So this is sine, not cosecant, but super helpful to graph it. Okay. Green. I'm going to do green for my asymptotes. Anywhere sine is 0, we can't divide by 0, so we have to mark those as our asymptotes. So, starting to construct this, and it's 0 through there, so I don't know if you can see that very well, but through x equals 0, we're also going to have a vertical asymptote. Just to keep this cool color scheme going, I'm going to go blue. Now, when we're graphing cosecant, it's going to be 1 divided by this function, so we're not going to be able to perfectly match everything, but we do know the maximum and minimums are 1 and -1. 1 divided by 1 is 1. So cosecant actually matches up with that point. 1 divided by -1 is -1. So cosecant has these coordinates in common. as sine. And then, if you think about dividing, 1 divided by a fraction, or 1 divided by, say, a half. 1 divided by a half is 2. So something like that. 1 divided by a half is 2. So it does this little thing. Almost looks like a quadratic, kind of like how cotangent and tangent look like cubics. It's definitely not, but looks that way. So this would be, air quotes, your vertex, and then it shoots out like that. Same thing down here. We have these values here, and connects like that. I want to make it clear, this is one cycle. This together, these two air quotes quadratics are one cycle, or it's one cycle here, because it doesn't repeat itself yet until we get over to this point. Okay, so these are repeated values. This is the end of one cycle. So this asymptote from this asymptote to this asymptote is one cycle. But you just have to repeat the process. Okay? So the blue is equal to cosecant of x. Everything else is just a guide on what to do. Okay? Very similar process. Secant is 1 over cosine, so think about tangent where those asymptotes are. Secant has the same asymptotes because that's where x is in the denominator. Both can't divide by 0. So cosine is 0 at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, anywhere on the unit circle where it's on the y-axis. So just keep that in mind. But same process as before. This time you're just going to graph cosine instead. So this time we're going to start, again, I'm going to make this 1, negative 1, pi over 2, and pi. Start at 1, and then going down, and then up, down, up, down. Show some love on the left-hand side. And we've got cosine. Now marking your asymptotes is wherever cosine is 0. The asymptotes should match tangent, because tangent is sine divided by cosine. So it can't exist when cosine is 0. Here's our asymptotes. Now graphing secant. Again, 1 divided by 1, still 1. 1 divided by negative 1, still negative 1, and so on. So these coordinates are going to match. Make sure you're not trusting your sloppy graph. If it is sloppy like mine, the midpoint between the two should be your air quotes vertex again. Same thing, should look like a bunch of quadratics stacked on each other or next to each other. Reason we know they're not quadratics is there's doesn't have vertical asymptotes for a quadratic, but just filling it in. If you wanted to be more precise than me, then you want to look at pi over 3, so a third is right about there. 1/3 should be at 2, so mine looks pretty good. Negative pi over 3 should also be at 2. It's close, but if I was to grade a graph, I'd make sure that I'm seeing cosine, I'm seeing the asymptotes, and then I'm seeing the starting points and that they're going off in the correct direction. But nothing else to graphing these. Again, sine and cosine are super helpful when you're graphing. On your graphing calculator, probably the part that you care about most is so you can check your answer. You don't have buttons for these unless you have a different calculator than I do, or you actually found them. I don't think they exist on my calculator. So if you're like me and you don't know how to find it or they don't exist, go back to what these functions are. They're the reciprocals of the big three. So reciprocal of tangent is cotangent. So what you would type into the y equal screen is 1 divided by tan of x. Make sure you're in the correct mode. Radians, we graphed all of ours in radians, so you want to make sure you're in radians mode. Cosecant is the reciprocal of sine. So if you do 1 divided by sine, you have cosecant. And then 1 over secant. Or sorry, secant is 1 over cosine of x. Okay. Do 1 just for fun. But this is cotangent. But let's do a more exciting one like sine. Graph. So you can see a bunch of those quadratic looking items. Remember, your calculator starts to not like the asymptotes, so you might see some rounding here. Looks like it got chopped off a little bit. Over here it looks okay outside of that. Just for fun, we can type in sine of x as well. You can see it just going in between those vertices. Should look very similar for the cosine. I'll let you try that out on your own if you wanted to. But if you ever wanted to type in secant, cosecant, or cotangent into your calculator, you need to do 1 divided by whatever one you're working with. That's all I got for you today. This is the last one of the week. Make sure you're clicking turn in on Google Classroom to show me that you've done the 30 minutes for each. If you're doing the college now, make sure all of those assignments are done before Sunday at midnight. But until next week,